everyone. Thank you guys all so much for joining. Today, our speaker is going to be Dr. Muzzamal Shaukay from Texas A&M University. He is a postdoctoral research associate working in the Institute for Quantum Science and Engineering. Today, he's going to present on stimulated Brillouin scattering gain with BJK velocity dependent relaxation time. So this is in regards to our laser driver physics within the RISE Hub. So with that, I'll let Muzzamal take the floor.
Thank you. Thank you, Kavita. And good afternoon, everyone. And thank you, Kavita, and everyone asking me to present this research work here. So I would start with that. Around 2 months ago, in the month of July, in this seminar series, of course, Kavita has presented some experimental results regarding the stimulated Brillouin scattering gain in comparison to the theoretical observation done by Everbach in 1975. So the motivation of my presentation is to let all of you know that how to enhance that SBS gain with the inclusion of velocity dependence in the relaxation time of the BGK model. First of all, we will discuss briefly what is stimulated Brillouin scattering and what the collision terms looks like in the BGK model, which is very important, but after reviewing some literature briefly. Then we will discuss in detail what methodology has used by the Everbach to obtain the stimulated Brillouin scattering gain. Then what changes we have predicted or done to observe that how to enhance that stimulated Brillouin scattering gain. After that, we will see that the very interesting results of theoretical comparison and some comparison with the experiments done by the Kavita and Stephen, especially from University of Illinois. And at the end, I would also like to share with you the binary mixture of gases analytical expression, which is so far I have obtained. That is not final yet, but I would like to share because in future, Professor Gary Eden was asking me, okay, they are thinking to do that experiment nearby future. And at the end, we will summarize our results. Let me start with a very fundamental Boltzmann equation, which we cannot solve until we know the specific form these two terms. Term one is the force and term two is the collision term. Many researchers have described these two terms in a different way, whatever they want to study, and some in fact ignore that collision term to assume that Coulomb interaction between the particles to make this equation the Vlasov equation. But for us, this collision term will be very, very important, which you will see in a moment. Or if simply I would say that in the focus of my whole presentation is how to play with this equation, basically, that you will see that in the whole presentation. To understand the stimulated Brillouin scattering process, the first process is the electrorestriction, in which the materials become compressed in the presence of electric field. What I mean to say that when a dielectric slab placed in the fringing field of a parallel plate capacitor, the slab will experience a force tending to pull it into the region of maximum field strength. I mean, in the presence of an electric field, you will feel that you will observe that the molecule develops a dipole moment P with a stored energy of this particular form, epsilon 0 alpha E square, due to which you can determine this force, which is the electrodestructive force, by saying that the gradient of the electric field square. And this is very important, which I was telling you, the term one. It is important in the stimulated Brillouin scattering process, basically. And stimulated Brillouin scattering is a non-linear process in which involves the interaction of light with the acoustic phonons, and it generates the backward scattered wave E2 with an accompanying phonons or the acoustic wave having some frequency omega, capital omega, and wave vector k and the density rho. And all this process of the coupling between the optical fields and the acoustic waves occurs via the process of electrorestriction, which I was telling you that one. In other words, if I would say that, if you will see that a pump is incident on the SBS cell and it reaches to the focus, it will generate sub backward scattered wave, and it will shift its energy to the backward scattered wave, and at the end you will see that large peak or the sharp rising edge of the Stokes wave. And of course, all this process involves the conservation of energy and momentum, due to which we can determine the billion frequency of few gigahertz by using this phase matching condition. This is the whole process. Of course, I am telling you just the simply, but this whole process involves a lot of mathematics, which I am not describing in detail here. You can find in a very similar, very simply in a literature, especially in the Boyd book, or many other researchers have predicted many others elsewhere. But of course, why I am not predicting these theories here, because I have already a lot of mathematics. After a few slides, you will see that. So at the moment, I would say that let me ignore this mathematics involved for the stimulative balance scattering process here. But the main motivation was the conservation of energy, phase matching condition, and what is the stimulative balance process that I told you. Another important point is to determine the Kulian term. We need to differentiate first the hydrodynamics and the kinetic theory by using this time scale of the characteristic time, or the mean free time, or the mean free path. With respect to that, many researchers have predicted many interesting results for the hydrodynamics or the kinetic theory. However, in the intermediate range, where the characteristics time is of the order of the mean free time or the mean free path length, then we need to specify that collision term in a very specific way, which is basically BGK predicted. And then the question comes with what that BGK is. BGK is basically the name of three scientists, Bhatnagar, Gross, and Crook, who predicted that the collision term in terms of the relaxation time. Initially, they were asking that this relaxation time depending on the velocity, but due to the complexity of the problem and the charge conservation, they ignored that dependence and assumed that this tau is constant in time, this constant relaxation time. So they make it very easy to solve this dynamics, what they were studying. But later on, for many researchers, in fact, this was very interesting model to study many interesting research what they have already studied, many researchers. And one was the scientist Morse, who studied this model with the inclusion of the internal degrees of freedom. And he assumes that there is an equipartition of energy between the internal and translational degrees of freedom, due to which we have to uh, parameterize this collision term in a different way, like elastic and inelastic collision, where due to the equipartition of energy for the inelastic collision, this inelastic will come with the total temperature, which is not hold for the elastic collision. So due to which we have to present the elastic collision with two different temperatures, due to the inclusion of the internal dynamics. That means one is the translational temperature, or other one is the internal temperature, if we are considering that internal. If we are not considering, of course, internal temperature, then it will be ignored. But in this model, he assumes that. Now, now that's the time with which we have to understand that basically what theory we have predicted. It's better, or to understand that theory, we need to initially understand what the theory has predicted by the Everbach without velocity independence, they assumed. In fact, the Everbach used the theory of Morse. If you will see this model equation, which is exactly the Boltzmann equation, which I was telling you, that they will f of L tilde, which is representing the distribution function, f of z is the force, and the right side term is the collision term. And this collision term is representing in terms of the elastic and inelastic part, inelastic collision relaxation time, what the Morse has done. But and this M of t is basically the simply the Boltzmann distributions with respect to that one. And the psi L represents the energy of that rotational states, because we are assuming the internal states. Here, if you will see that M of t, which is M subscript t, t mean translational dynamics. This depends on two different temperatures. One is the T phi T sub T, which is the translational temperature, T sub I, which is the internal temperature, because of the equipartition of energy that comes here. But for the internal dynamics, because of the equipartition of energy or the relaxation of the dynamics with the inelastic collision, This depends on the total temperature. But of course, there is some relation between the total temperature with the internal temperature and translation temperature. We can use that later. But if you will see that one, let's say that, let me ask someone, or let me say in a way that if you will see this whole Collian term and you will see this model equation, can we solve this equation? Is it not look very complicated at the moment? So first question was that how to simplify that question, though that Collian term, to see some dynamics in the equation. And for that, we introduce small perturbation with respect to the distribution function, where this first term is the zeroth order with respect to the distribution function, and the plus n0 f of L, that is the first order perturbation with respect to the distribution function. So now the question comes with that, is that we need to, do we need just one perturbation? Is that enough to solve the dynamics? So the answer is that yes, we can use this perturbation with some density perturbation to solve the dynamics or TC, see the stimulated Brillouin scattering gain. But is that enough to do it experimentally, or the already experimentally predicted results by the Stephen or Kavita or other group fellows? Is that enough to see those dynamics? So I would say that no. And for that those dynamics, to see those dynamics, we need to include all these perturbations with respect to the density, velocity, and the temperature. And not temperature is not just the translational temperature. Internal temperature, translational temperature, and total temperature. All this includes with that perturbation. So, of course, now the life becomes more complicated, but looks simple with that Cloyan term. If you will see that after using that perturbation, we simplify those dynamics, we will see that we have this simple Cloyan term, which seems to be interesting in a way that we can see something there. It comes with the relaxation time, with the four terms, the density, local velocity, translational temperature, internal temperature. But here you will not see any total temperature because we use that uh, some relation between the translation and internal dynamics to the total temperature to 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 overcome that term here. And CV, of course, denotes the specific heat here. But now you have some specific term to understand that how to solve or how to play with that Boltzmann equation. Now comes to the other term, which is the force, basically. And this force, of course, comes with the two opposed wave, which comes with the stimulated Brillouin scattering process, means to say that incident beam generates a sound wave and a Stokes beam propagating in the backward direction, in which we have one is represented by the E1, which is the pump wave, and E2, which is the scattered Stokes wave. The combination of these two will come with F is equal to minus del U, which I was gradient of U, which I was describing last on the first slide or few slides before, that you can determine the force. Very simple. And what the question was, I was telling you that you cannot solve the Boltzmann equation until you have specific form of these terms, whatever the specific form you are using to study the dynamics, what you want to study. And now we have both force and the Collian term here. And now we can say that we have some terms, of course, simple terms, we can solve that terms. And to solve that term, we need to first determine the distribution function amplitude, f of L. We don't know what is f of L yet. And for that, we introduce the slowly varying amplitude approximation for all the terms. For all the terms mean to say that for the density, for the velocity, local velocity, for the temperature, internal temperature, total temperature, and everything else. We introduce that factor and we find out, simplify that expression to find that what will be the amplitude of that distribution function, where this JC is basically the Collian term, but without the sigma f of L term here. If you will see that this Collian term comes with the first term minus sigma f of L, which comes after solving this sum in the combination of f of L bar, the amplitude of that distribution function. It comes to that one. The other factors of the JC remains the same with some amplitude of that factors come here. Now, of course, this is important. This function, why this function we need to find? Because we are interested to determine the moments of that distribution, the zeroth order, first order, second order, with respect to the temperature, velocity, or the density. And for that, we need to have that amplitude of the distribution function. And of course, if you will see these movements of these zeroth first order and second order, you can see that you need to have that f term here. You cannot predict anything until you know that f bar, f of l bar, that determines that. And now the comes with the to solve these dynamics, a lot of mathematics, of course, much mathematics involved. You need to be very conscious about plus minus signs, especially, or playing here and there to determine this 4 by 4 matrix for these four moments of that one, for the density, local velocity, translational or internal temperature. And of course, if you will solve that, you will come with a very simple expression of the density, perturbed density, that is depending on nd parameter, which nd means to say that numerator over denominator. And this numerator over denominator is a simple factor which is just the depending on the frequency of the phonon, translation relaxation time, or the ratio of these two relaxation times of the internal inelastic or elastic collisions, or the specific heat. If you will see this alpha term, delta, x and y in all these expressions. Another term is the w, which is the error function, which is defined. And z is, of course, is x minus iy. Everything is including here. This expression is looks very simple. Now is the part to see that if we use how to obtain the gain of the simulated Brillouin scattering. This is, of course, the process which I ignored to explain you at the start. Like that, you have some Maxwell equations. With Maxwell equations, you will form that wave equation with some polarization P here. And after using some mathematical details which you can find anywhere in the literature, you can determine that gain very easily by using this factor. Of course, this there is a factor of frequency of the stroke wave. There is a factor of polarization here. There is a factor of density here, which is important at the moment, which is important. But at the moment, I am saying that for theoretical perspective, for me, the theory was mainly comes with the kinetic process, which is important is the density, perturbed density. And that perturbed density, I have shown you that on the last slide, depending on this parameter nd, which is gain is proportional to imaginary nd. Of course, I already told you that this imaginary nd mean the dependence on the frequency, relaxation time, and specific heat. Now comes to see that what will happen with these four perturbations. First, I want to let you know that uh, this is the part of the gain of the stimulated Brillouin scattering gain, which is depending on the numerator over denominator versus the frequency of the normalized frequency of the phonon for different values of the relaxation time normalized with respect to that factor. And if you will see that as we increases the y value, the more collision in a system, you will see the narrower peak you have and more gain you can get that one. But this all these details, I want to mention that I was telling you why we need that four perturbations. If we do not have those four perturbations in a system, minimum three or four, with respect to that one, we cannot see this observation. We will see the inverse of that if we assume just the distribution function or the density perturbation and ignore the velocity or the temperature perturbation. We will not see these results here. We will see the inverse of those. This is important. And another point is that this is for the diatomic gas. What the mainly the Everbach has assumed or considered for the nitrogen N2 gas for these parameters of the alpha equal to 1 over 5 and specific heat ratio is the 2 by 3, specifically for the nitrogen gas at the moment. Now, the theory, you know that what the Everbach has done, and you see that what the results they obtained. Now comes to the point that what we have done and what we have predicted. And for that, we of course use the same model, whatever the Everbach has used or the Morse has considered, like the elastic part and inelastic part. But now we replace that relaxation time with the inclusion of the velocity instead of independent of velocity. And that dependence comes with that this relaxation time for elastic or inelastic comes with the linear velocity, linear dependence on the velocity normalized by this V naught factor, and have some extra beta parameter, which is the free parameter I am considering, which we can adjust in accordance to the experimental requirement. What I'm thinking that. And if you will see that now the point is that one, if beta equal to zero, this beta equal to zero mean you have exactly the results of Everbach. But if beta is something, so it means that you have some dependence on the velocity factor. What that beta comes with that? It's a free parameter. That's what I am telling at the moment, assuming that one. Of course, there is much complications involved than the Everbach paper, but the process is exactly the same. So I will not explain what will happen. Exactly follow that process. Complexity of the problem, of course, comes with that. Use some more tricks or assumptions, you will get that expression again, numerator, no, num over den. Now numerator over denominator goes to num over den because this num over den comes with many other factors, a, b, c, d, x, y, z, x, etc., etc. Now the question is that this expression looks much complicated. Of course, it looks complicated, but it is very simple. If you will see that what the extra parameters, if we can see that a, b, eta, m, chi, n, etc., etc. No, they all depend on x, the frequency of the phonon, the relaxation time, specific heat, and one extra parameter, which is beta, basically. This beta creates that complexity of the problem. If you will see that beta equal to zero, you will have very simple numerator over denominator expression. But the magic of this beta comes in the next slide. Now we'll see that if beta equal to zero, mean Everbach results, what the Everbach has predicted. And if beta is something, which is assuming I am very, very small value, but it enhances the simulated Bayesian scattering significantly. And also there is some question that at the start, if you will see that there is some more scattering with the beta parameter, that in fact comes with the scattering comes because of the density dependence on the temperature variation. Temperature variation mean if you will see that 4 by 4 matrix, I was telling you that then you have the simultaneous four equations which you need to solve. Because of that density dependence on the temperature, translational temperature or internal temperature variation, that scattering comes with that, which you will see more significantly after few slides. This was the comparison with Everbach for the nitrogen gas. Exactly. But can we use this theory for the monatomic gas, like krypton, argon, or whatever we want to use that for? Yes, of course. You can use that one. For this moment, I am using the krypton, but we can use any gas, any model which we want to use. And if you will see that the similar behavior exactly for the diatomic gas, but it enhances that more than the diatomic gas for the krypton monatomic gas. Similar behavior. Now the question comes with the collision cross-section point of view. That mean to you all of you know might know that the collision cross-section is a basic fundamental theory to predict the collision relaxation time or the scattering rate used in the kinetic theory basically. And for that we represent that collision or the relaxation time in terms of the density, collision cross-section, or the relative velocity. That is defining a density is defining in terms of the gas law, V relative defining by this temperature factor with the mu is the reduced mass. And collision cross section, fortunately, we find exactly from these papers. What about for the nitrogen, especially? I would say that at the moment, for the elastic and inelastic light, they determine that range of this collision cross section. And then we, of course, you can see that all the factors we have that dependence on the density, and now it comes to the pressure P. And for that variation P, we see that as we increase the pressure, we have more gain in the system. And with increasing pressure, uh, our gain is shifted to the higher frequency. If you will see that, that is a theoretical perspective. For the net, again, this is for the nitrogen gas, diatomic. Again, simple. If you will see that the variation of that one, There is less scattering for the diatomic, but more scattering for the monatomic gas. And this comes with the part again, for the pressure term, more pressure, you have the more gain and more frequency shifted towards the more frequency, that one. But again, I want to emphasize that at the moment you have seen that ND, imaginary ND. This means that I was telling you initially that gain is proportional to ND, numerator over denominator, num over den or denominator over denominator. That is just this factor. I am not assuming any numerical values for the Stoke wave, the frequency, density, or whatever I need to have that one till now. Now comes to the point for the monatomic or diatomic part here. And here, if you will see that for the monatomic, we have the more gain. For the diatomic, we have less gain, as is confirmed very simple. The results predicted by the Kavita 2 months ago, that we have experimental krypton has better, or the monatomic gas has higher gain than the nitrogen or the diatomic gas. And this beta parameter, last point of that part, is beta variation. Of course, beta is the main parameter which we have included, that beta. If you will see that the more beta you have, the more gain you can have. But with that more gain, you have more scattering. So it means that we need to choose that beta parameter very carefully to have that experimental observation uh, for that one. Another point that I did not mention before, that the frequency of the phonon is in gigahertz, exactly within the range of what I was predicting, that with the phase matching condition, you can have that value in the gigahertz, few gigahertz range. Now it's come to the point to compare our theoretical and experimental results basically. And for that, I am, of course, thanks to Kavita or the Stephen for giving me that results or permission to share these with you guys here. Uh, Special for the, let me tell you first for the theoretical comparison. If you will see that at different pressure, for beta equal to 0 mean Everbach theory and beta equal to something mean, whatever that something, you will see different parameters here, but that beta something mean our results. If you will see that at 1 or 2 atmosphere, there is no change with that beta parameter. But as we increase the pressure, we will have significant change in the gain. And another point is that one, if you will see that with the inclusion of that beta, you are shifting curve to the left of that side, to the left of that. Okay, this is important, this is very important. After you will find some 1 or 2 slides later, you will see that again, this is for the krypton gas. Okay, but for the nitrogen, and if you will see again, it follows the similar behavior for the two. 1 p is equal to 1 atmosphere or 2 atmosphere, it's almost the same. But as we increase the pressure, you have more gain, and more gain and shifted towards left side of the curve, or towards less frequency. In other words, left side mean to say that. Why I'm emphasizing the left side, I will show you after 1 or 2 slides, might be that one. Now comes to the point with the experimental results done by the Stephen. That is the red curve. If you will see that uh, experimental data, thanks for sharing with us and allowing us to show here. And then the other curve with beta equal to very, very small at pressure 6 atmosphere, we have that one. And you can see that the results matches much better way, much better. Again, we have a different, if we increase, but beta is very, very small here. But if you increase some beta, you will have that something shift here towards a less frequency with respect to beta parameter, increase in beta parameter, again for the krypton gas. Similarly, if you will see this nitrogen gas, it is very important. For the same parameters as the monatomic gas, you will see that this is more or less exactly matching with the experimental results in a way, with a peak exactly at the point at beta equal to 0.009. That is exactly peak matches with the experimental predicted results. And it follows the back behavior exactly the same, almost the same like experimental predictions. They have done uh, the results obtained by the Stephen. Now again, this result, thank you Kavita and Stephen allowing me to show this curve here. This is the curve, which is not, of course, mine. The Kavita has shown you around 2 months ago. If you will see this curve for the krypton, red curve, experimental, and the solid curves, black, everywhere is for the theoretical. Uh, Theoretical mean beta equal to 0. That there they have shown here that curve here. And if you will see for especially, let me emphasize on the krypton first, other than for the moment later. If you will see that the krypton has the wider expression for experimentally and less wider for the theoretical perspective, a mean inside of that one. What I was telling you that the shifting towards left. And if you will see that for the krypton gas in beta equal to some value, of course I can change that value, but I am predicting some results here. This left side, what I was emphasizing, that less frequency or towards left side because of this curve. What I have seen experimentally predicted result that if the theoretical observation is on the right side and experimental is on the left side, uh, already predicted by the Stephen or collaborators, now we have that theory beta with which we can shift towards left something by using carefully what beta parameter we need to choose for the krypton. This is for the krypton. But now comes to the nitrogen gas. If you will see that nitrogen gas, it it almost not matches, or somehow you can say that this is not predicted experiment. Theoretical prediction is not very good with the experimental, uh, or whatever they have predicted. But now comes to this point here with the same value. You will see that it is exactly meeting to the gain, maximum gain value that you have, exactly matching with the experimental results. Initially, it is not somehow, but after that point, it comes to that point. But again, careful observation of that beta parameter that we might adjust sooner or later, that one. Uh, Here, before summarizing my presentation part of this one, I would say that for this specially experimental and theoretical comparison, which I am predicting on this slide, basically, this is done, of course, myself done by these two parts, and the other one experiment done by the Kavita and other Stephen. Uh, we need to have some meetings for that one, of course, before finalizing everything. And we will sooner or later we will have some meetings to emphasize that if there is something wrong with us or something mistake or whatever we have predicted. So we will sooner or later we will get some meetings uh, to observe anything or to confirm everything. At the moment, I would say that. So summary of this part, I would say that the velocity dependent relaxation leads to significant modification in the gain spectrum, which you have seen, and exactly matching or more or less better, uh, getting the better results with the experimental observation. And then I would say that this means that our findings or the inclusion of the velocity dependence offer new insight into the kinetic effects and provide a potential new parameter for the engineering effort to to observe that how to play with this laser fusion in future. This was the part which I was interested to share with you, not in much details, but I would like to share that as well because of my discussion with Professor Gary Eden. He was telling that sooner or later they are interested to have the binary mixture of gas. They want to play with that, and they want to see that what will happen uh, with the exposure of this binary mixture of any two gases, and what type of uh, gain or in other words, what the significant changes they can observe experimentally for that. And then I thought to work on that one. And I was fortunate enough to find this paper of the Gross and Crook. Now this is the GK, not BGK, basically, but Nagar is not here. And they assume this binary mixture of the two component system. Exactly the theory is the same, but now they have included the relaxation time of interparticle or relaxation time for the interspecies, basically. And which you will find in a moment in a very clear way. This is the paper basically they have, which I am going to show you the reference of that one. Another one very interesting paper done in 2022 by some Italian scientist, that Q11 mean say that the interparticle interaction of the collision. Q12 mean that interspecies collision, mean gas 1 or gas 2. Similarly, Q21 and Q22 interparticle interspecies that comes with that. And this new IK mean 1 over tau, which is the frequency over is equal to 1 over time. Again, then I thought to proceed very simple way, uh, to consider and ignore the inelastic part now. And instead of inelastic part, I just assume the interspecies, tau ij. Interspecies mean gas 1 and gas 2 relaxation time, collision relaxation time. And then, of course, solve everything is similar to what I have predicted with the Everbach theory. And then you will have some more relation with respect to Tij mean gas 1 or gas 2, which have some factors. And again, there is a mass between the issue between the difference between these two gases. Can it is possible to have same gas or different gases for that one? Of course, the same gas will give you the same results already, but for different gases, what will happen? Then collision terms looks like this one, and in which you can see that sigma ij mean to say that the interspecies relaxation, the difference, I'm just predicting the difference of that one, interspecies and so on. Now it is much more complicated. Instead of 4 x 4, you have 6 by 6 matrix with some, you will see that this is the two slides expression. This one expression comes with the two slides basically, and you will get that gain. And that gain depending on two way. One is the R1 and R2. Both R1 and R2 depending on the relaxation time, interspecies relaxation time. And that the theoretical results, of course, I have predicted so far, analytical results so obtained, and some of the graph, for example, that if we ignore that interspecies interaction, we should have the very similar results of the Everbach like that, or with respect to that, if we ignore the beta factor. Similarly, but if we have that mass dependence, because if you will see that expressions, the mass was very important, Aij, Bij, and every curve in these uh, R and R1 to R2, you will see that there are many terms, too many complicated terms here. You will see that one. And for that, if you will see that if we increase the mass, for the same mass, of course, you can get that expression. For the different masses, you will see that the scattering becomes important. More gain you have than that, this one, but you have more scattering here. And if you will have increase the mass more, like 1.5 times of the mass of one, then there is more scattering involved in the system. This is the prediction yet at the moment. But of course, the results are not final yet. Everything else is not final. I reached to this point and to till now. So I would say that at this point we have other cases to understand and discuss. Then we will go to the experimental perspective to confirm that one. But for this, all this summarized to all these results, I would say that for the binary, especially for the binary mixture of gases, we need to be very careful what type of gases we need to choose, especially with respect to that mass, that it plays very important role, and other properties of those gases. We need to understand first to do that experiment. Thank you.
Thank you, Muzzamal, for an excellent talk. So with that, let's take any questions. You're welcome to drop them in the chat, either privately or to everyone, or unmute yourself.
Hi, can you hear me?
Yeah, we can
Yes.
hear you.
Hi, Shaukat, nice talk. I have this question like you consider in the binary mixture M2 equal to 1.1, M1. So how would you put in terms of densities? These are the masses that I understand, but what about the
Yeah.
density mixture?
Yeah, of course. I was telling you that one, if you will see these expressions, there is a much more complications involved here, which I ignored to show more mathematics because for that one. This is long mathematics. If you will that density, Mij depends on Ni mean the density. That is the different densities for two different gases. I am predicting just one thing here because I was focusing, if you will see that G is proportional to imaginary R. And here I am just predicting these results. But when you will not ignore the proportionality factor, which is basically depending on the density, and that density comes with the pressure, of course, that will be very important.
Okay, thank you.
I actually had a question on the binary mixtures as well. Could you go to the plots that you made? I think on the next slide or that, yeah. So, how does the gain compare? I know it does depend on obviously which gas, but how does the gain compare of the binary mixture compared to a single gas?
So say it again.
How does the gain compare of a binary mixture compared to like just a single gas?
This one is the single gas. You can say that.
But
Okay.
yeah, how
This is
does the gain compare? You have imaginary R. Like, what is the gain? Like, how did they compare to one another?
yeah, that I am telling you that one. If you will see this curve here,
Yeah.
okay, if you will see this curve, the you can see that, okay, let me say in that way that the maximum gain for one y equal to 5, let's say that you have around 3, okay, 3 in terms of
Mhm.
that gain. If we will parameterize that one with experimental values, then we can of course have dimensions as well. Let's say that this is the number 3, and here if you will see that at the exactly the range of that parameter is not same. Why?
Mhm.
Okay,
Mhm.
that's y is equal to 1.3. That comes with very important here. Okay, you cannot have that y equal to goes to the 5. You cannot go towards that one. Why? Because the scattering will be very important, or this
Yeah.
observed or this behavior will be the inverse of that if you will go beyond this range 1.4, 1.5, or more than that. Then you cannot analyze that perfectly.
I see. Is it because you're in the hydrodynamic theory at that point, or like
No.
the hydrodynamic regime, or is it just
No,
the
it
physics
is the
is
same kinetic process.
okay, okay.
But that comes to the factor that we have some inclusion of that density or the temperature perturbations.
Hmm.
But here, if you will see these expressions, this Tij, that is Bij, and Bij comes with the mass. And here, this the Qj, Qy, that comes with the velocity basically. But that factor will not be important because we are assuming that the perturbation in the velocity is ignoring the zeroth order and considering the first order. But if we consider the zeroth order, here it will be very, very important. And all these dynamics will come part. Very important.
I see. Thank you. There's also a question in the chat.
Okay.
So I can read it out loud. Would operation in high collisionality regime, so y equal 5, be practical, or does it introduce unwanted damping or losses elsewhere?
Yeah. Okay. I would say that uh, with respect to, if you will see that comparison with respect to the experiment, because theoretical prediction are different than the experiments, of course. We have done that theoretical observation with respect to that if we are having some y or the relaxation more collision in a system, then you have more gain. But if you will convert that more collision with respect to that pressure, which I have shown you that the more pressure you have, and then you have more gain with respect to that. It means that you have more pressure, you have more gain. But that comes to the point that can you go much higher pressure, which is exactly the y. In other words, theoretically, we can say that that is equal to y. So, no, I would say that no. It depending on the basically the conditions, because if you will go that, then the scattering will be important, and that scattering will be important, and then in terms of the theoretically, and then you will not have that gain, of course. And experimental point of view, if you have that pressure, you cannot play with much higher pressure. Of course, the experimentalists knows
We
better than the person.
we could, I mean, not with our setup, you could get to high pressures, but the problem that
No.
you're going to run into is breakdown voltage.
Yeah,
Your
exactly.
breakdown
You can
voltage
get higher pressure,
decreases.
but yeah,
So,
exactly.
yeah, but great questions. Are there any other questions from the audience?